Have you ever just, stopped and really thought about sound? I mean, it's everywhere. Music, voices, the noise of traffic. But what is it? How does it actually work? Well, today, we're going to break it all down. We're going to follow the journey of sound, right from a tiny vibration all the way to the sensation you get inside your head.
So let's start with the big question. What is sound, really? Is it a physical thing that's flying through the air? Is it some kind of invisible wave? Or is it maybe just something our brain makes up? Well, the truth is, it's kind of all of the above. And we're going to figure out how.
All right, our whole journey starts with a surprisingly simple concept. A fundamental rule, really. Every single sound you have ever heard, from the quietest whisper to a massive thunderclap, every single one starts with a vibration. Now, how can we prove this? Check out this classic experiment. You strike a tuning fork, and you hear that perfect, clear tone. But you can't see it moving, right? Well, if you take that vibrating fork and just gently touch it to a little suspended ball, bam, the ball gets kicked away. That right there is the proof. It's the physical evidence that the source of that sound is in constant, super fast motion. It's vibrating. And really, that's the main takeaway for this first part. Sound is born from vibration. A guitar string, your vocal cords, a drum head, they all have to be in that rapid back and forth motion to make any sound at all. It is the one essential ingredient.
Okay, so an object vibrates. We've got that down. But how does that vibration get from way over there all the way to our ears? That is the next piece of this amazing puzzle.
You might imagine that when you hear something, little particles of air are literally flying from, say, a speaker directly into your ear. But nope, that's not what's happening. It's the disturbance, the energy that travels. Think of it more like a chain reaction. One air particle bumps into its neighbor, which bumps into its neighbor, and so on, passing the energy along. Each particle just kind of wiggles back and forth and then settles right back where it started.
You know, the perfect way to picture this is with a slinky. If you push one end, you see that wave of energy zip all the way to the other side. But if you watch any single coil on that slinky, what does it do? It just moves a little bit forward and a little bit back. That's exactly how sound travels.
So as that tuning fork is vibrating back and forth, it's creating this really cool pattern in the air. When it moves forward, it squishes the air particles together, creating a little zone of high pressure. We call that a compression. And when it moves backward, it leaves a gap, a zone of low pressure, called a rarefaction. And this repeating pattern, compression, rarefaction, that is what we call a sound wave. The fancy scientific name for it is a longitudinal wave. And that just means the particles are wiggling back and forth in the same direction that the wave itself is traveling, just like that slinky.
So, think about it. A violin sounds totally different from a foghorn, right? What gives every sound its own unique character, its own fingerprint? Well, it all comes down to the specific properties of its wave.
When we hear a sound, our brain mostly cares about two things. Pitch, is it a high sound or a low sound? And loudness, basically its volume. But what's actually happening out there in the physical world that creates those feelings for us? This is where it all connects. Pitch is all about frequency. That's just the number of vibrations happening every second, and we measure it in hertz. So faster vibrations give you a higher frequency, which your brain hears as a higher pitch. And loudness? That's all about amplitude. That's the size or the sheer intensity of the wave. A bigger, more forceful vibration makes a bigger wave, and that's a louder sound. Simple as that. And just to put this into perspective, the typical range for human hearing is pretty incredible. We can hear frequencies from a super low rumble at just 20 vibrations per second, all the way up to a really high-pitched whine at 20,000 vibrations per second. That's a huge range.
Okay, so we know how sound is made and how it travels, but what happens when that sound wave runs into a wall? And what about all the sounds out there that we can't even hear? Let's dive into that.
An echo is really just a reflection. It's that simple. Just like light bounces off a mirror, sound waves bounce off big, hard surfaces, like a cliff face or the side of a building. And this exact idea, this principle of reflection, is what powers everything from a submarine's sonar to how a bat sees in the dark with echolocation.
Have you ever wondered why you only hear really clear echoes in big, open spaces? Well, here's a fun fact. For our brains to actually hear a distinct, separate echo, the thing that the sound is bouncing off of has to be at least 17.2 meters away. Why? Because it takes our brain about 1/10 of a second to process the original sound.
If the reflection comes back any faster than that, our brain just mushes it all together into one sound. Now that range of hearing we have, it's just a tiny, tiny sliver of all the sound that's actually out there. Frequencies that are too low for us to hear are called infrasound. Animals like elephants use these low rumbles to talk to each other over huge distances. And frequencies that are too high for us, that's ultrasound. Bats and dolphins are famous for using it to navigate and hunt in the dark.
And it's not just animals. We humans have figured out how to use ultrasound in some absolutely incredible ways. We use these high-frequency waves to clean tiny, delicate parts, to find invisible cracks in metal, to create images of our organs, like a beating heart. We can even use them to break up kidney stones without ever making a cut. And, of course, they let us see a developing baby during pregnancy. It's amazing stuff.
So let's wrap this up by going back to that famous old riddle. After everything we've talked about, what do you think? If a tree falls in a forest and nobody's there, does it make a sound? Well, we know for a fact that the falling tree creates a physical disturbance, a vibration, a longitudinal wave traveling through the air. But if there's no ear there to catch that wave and no brain to process it into the sensation of hearing, did it actually make a sound? That's a good one to chew on.